The properties exhibited by colloidal solutions can be classified as colligative properties, optical properties, mechanical properties, and electrical properties. Let us first discuss their colligative properties. Colloidal solutions exhibit the colligative properties osmotic pressure, elevation in boiling point, depression in freezing point, and relative lowering of vapor pressure, in the same way as true solutions do. However, the magnitudes of these properties for colloidal solutions are much smaller than those obtained for true solutions, and thus it becomes very difficult to measure them accurately. This is because colloidal particles, being bigger aggregates, have very high average molecular masses. Therefore, the number of particles in a colloidal solution is small as compared to that of a true solution. Hence, at a given concentration, the value of any colligative property of a colloidal solution is of a small order as compared to the value shown by a true solution. However, colloids exhibit measurable osmotic pressure, which can be determined with a reasonable degree of accuracy. This property of colloidal solutions is therefore used to determine the average molecular masses of certain colloidal particles, like proteins and other polymers. One property of colloids that distinguishes them from true solutions is the Tyndall effect. When a beam of light passes through a true solution, there is no scattering and the path of light cannot be traced. The solution appears clear if observed in the direction of light, and perfectly dark if observed from a direction perpendicular to the direction of light. On the other hand, when a beam of light is allowed to pass through a colloid, it gets scattered by the colloidal particles, and the path of the light can be traced. The path of light gets illuminated with a blush light. This phenomenon of scattering of light by colloidal particles is called the Tyndall effect. The illuminated, bright cone of light is called the Tyndall cone. Try to recollect that every time you go to a cinema hall, you're able to trace the path of the light beam from the projector. What you actually see is the Tyndall effect. A Tyndall cone formed due to the scattering of light by dust particles is seen in the movie hall. The Tyndall effect is observed only when two conditions are satisfied. First, the diameter of the particles of the dispersed phase should not be too small than the wavelength of the light used. This implies that this effect is observed when the dimensions of the colloidal particles are comparable to the wavelength of the visible light used. Secondly, the refractive indices of the dispersed phase and the dispersion medium should differ greatly in magnitude. The Tyndall effect was used to devise an instrument known as the ultramicroscope by Zsigmondy in the year 1903. The instrument is used to detect particles of colloidal dimensions. In an ultramicroscope, an intense beam of light is focused on a colloidal solution in a glass vessel. The solution is then observed in the microscope at right angles to the beam of light. The zone of light scattered by each individual colloidal particle is larger than the particle size. Therefore, a colloidal particle appears as a bright star against a dark background in constant motion when viewed through an ultramicroscope. Thus, we can say that the ultramicroscope does not render the actual colloidal particles visible, but allows the light scattered by them to be observed. It does not provide any information about the size and shape of the colloidal particles. The Tyndall effect also confirms the heterogeneous nature of colloidal solutions. Another important optical property of colloids is their color. Colloidal solutions are generally colored. The size, shape, and nature of the particles determine the color of a colloid. Larger particles absorb light of longer wavelength and therefore transmit light of shorter wavelength. For example, in a gold sol, if the particles are very fine, the sol is red in color. But when the size of the particles grow, the color changes to purple, then blue, and finally golden. The color of a sol also depends upon the manner in which the observer receives the light. For example, in reflected light, an aqueous solution of milk appears blue, whereas it looks red in transmitted light. Let us now learn about the mechanical properties of colloidal solutions. The continuous zigzag movement of colloidal particles in a dispersion medium is called Brownian movement. This random zigzag motion was first observed under a powerful microscope by the British botanist Robert Brown, and is named Brownian movement after him. Brownian movement is independent of the nature of the colloidal particles, but depends upon their size and on the viscosity of the solution. The movement of colloidal particles increases with a decrease in their size and in the viscosity of the medium. Brownian movement is caused by the bombardment of the molecules of the dispersion medium against the colloidal particles of the dispersed phase from all sides with unequal and unbalanced forces. This movement opposes the forces of gravity and has a stirring effect, meaning that the colloidal particles resist settling rapidly to the bottom of the vessel. Hence, we say that Brownian movement is responsible for the stability of a colloidal solution. Apart from exhibiting color, the Tyndall effect, Brownian motion, and colligative properties, colloidal solutions also exhibit electrical properties. The properties that we will discuss in this module are electrical charge on colloidal particles, electrophoresis, electroosmosis, and coagulation of salts. Let us first discuss the most important electrical property, the presence of electrical charge. The particles of a colloidal solution possess a definite electrical charge, either positive or negative on them. Due to the presence of the same charge, they repel each other and do not combine to form larger particles. This keeps them dispersed in the medium, and hence, a colloidal solution is stable. All the particles in a solution carry the same charge. The dispersion medium has an equal and opposite charge, Based on the nature of the charge on the colloidal particles, colloidal solutions are classified as positively charged or negatively charged sols. Hydrated metallic oxides like Al2O3, XH2O, Fe2O3, XH2O, and Cr2O3, XH2O, and basic dyes like methylene blue form positively charged sols. Starch sol, metal sols like copper sol and gold sol, metal sulfide sols like arsenious sulfide sol, and acid dyes like Congo red are examples of negatively charged sols. The electrical charge on colloidal particles may be due to several reasons. These include electron capture by the colloidal particles during electrodispersion of metals, preferential adsorption of ions from the solution, and the formation of an electrical. Let us discuss the most accepted reason first. The preferential adsorption of ions. Colloidal particles have the tendency to preferentially adsorb a particular type of ion from the solution. An ionic colloid preferentially adsorbs the ion common to the colloidal particles from the solution. For example, silver iodide precipitate adsorbs iodide ions from the dispersion medium if an excess of potassium iodide is used to prepare it. This results in the formation of a negatively charged colloidal solution. However, if an excess of silver nitrate is used for the precipitation of silver iodide, preferential adsorption of silver ions takes place, resulting in the formation of a positively charged colloidal solution. Similarly, a positive sol of hydrated ferric oxide is formed if ferric chloride is added to excess of hot water. This is due to the preferential adsorption of ferric ions. However, a negatively charged sol of ferric hydroxide is obtained when ferric chloride is added to sodium hydroxide. In this case, there is preferential adsorption of hydroxyl ions on the colloidal particles. In either case, the ions left out will give an equal and opposite charge to the dispersion medium and will remain in it. The positive or negatively charged colloidal particles of a layer attract oppositely charged ions from the dispersion medium, forming a second layer as shown here. These counterions are not absorbed on the surface of the colloidal particles, but exist in the solution. The combination of two layers of opposite charges around a colloidal particle is called the Helmholtz electrical double layer. The first layer is firmly held and is called the fixed layer, while the second or the outer layer is mobile and is termed as the diffused layer. The presence of opposite charges on the fixed and diffused layers of the double layer results in a difference in potential. This potential is called electrokinetic potential or zeta potential. Let us now discuss another electrical property of colloidal solutions, electrophoresis. The movement of colloidal particles towards a particular electrode under the influence of an electrical field is called electrophoresis. Electrophoresis helps establish the existence of electrical charge on colloidal particles. This property can also be used to establish the nature of the charge carried by the colloidal particles in a colloidal dispersion. The direction of movement of colloidal particles towards a particular electrode is governed by the nature of the charge on them. If the colloidal particles carry a positive charge, then they move towards the cathode when subjected to an electrical field, while negatively charged colloidal particles move towards the anode. An important application of electrophoresis is in sewage disposal. Let us discuss another electrical property, electroosmosis. If an electrical field is applied to a colloidal solution and a semi-permeable membrane is used to prevent the colloidal particles from moving, then the dispersion medium moves in a direction opposite to the direction in which the colloidal particles would have otherwise moved. This phenomenon is called electroosmosis. Let's define it. Electroosmosis is the movement of a dispersion medium under the influence of an electrical field when the movement of colloidal particles is prevented by a suitable membrane. Under the influence of an electrical field, the colloidal particles and the dispersion medium both have a tendency to move towards the oppositely charged electrodes. But the semi-permeable membrane does not allow the passage of the colloidal particles. The dispersion medium, however, can pass through the membrane and therefore its movement takes place. Another very important property of colloids is their coagulation, flocculation, or precipitation. You already know that one of the factors responsible for the stability of lyophobic colloids is the presence of charge on colloidal particles. However, if the charge is destroyed, they are free to come near each other to form larger molecules. These larger molecules aggregate or coagulate and then settle down under the force of gravity. This phenomenon is called coagulation or precipitation of the sol. The coagulation of a lyophobic colloidal solution can be achieved in a number of ways. One method is electrophoresis. You know that the colloidal particles in a colloidal dispersion move towards a particular electrode under the influence of an electrical field. If the process is carried over a prolonged period of time, then the colloidal particles get discharged at the oppositely charged electrode and get coagulated. Another method used to bring about coagulation is by mixing two oppositely charged sols. Mixing equal proportions of two oppositely charged sols neutralizes the charges either partially or completely, and thus causes the colloids to coagulate. For example, if equal proportions of a positively charged sol of hydrated ferric oxide and a negatively charged sol of arsenious sulfide are mixed, Then, the coagulation of both the salts takes place. This type of coagulation is called mutual coagulation. A sol may also be coagulated by simple boiling. When a sol is boiled, the adsorbed layer on the colloidal particles is distributed because of the higher number of collisions with the molecules of the dispersion medium. This reduces the charge on the colloidal particles and ultimately leads to precipitation. Arsenious sulfide sol undergoes coagulation on boiling. The coagulation of a sol can also be brought by persistent dialysis. You already know that traces of electrolytes are essential for the stability of colloids, since they get absorbed on the surface of colloidal particles by giving them charge. If the electrolyte is removed completely by persistent dialysis, then the colloidal solution would become unstable and undergo coagulation. The most important and useful method of coagulating sols is by adding an electrolyte. While traces of electrolytes are essential for stability, adding substantial amounts brings about the precipitation of colloids, as it completely neutralizes the charge on the colloidal particles. The ion responsible for causing coagulation is the one that carries a charge opposite to that present on the colloidal particles, and is known as the coagulating ion. For example, a positively charged sol gets coagulated by the negatively charged ions of the electrolyte that is added. The coagulation behavior of different electrolytes can be explained on the basis of the Hardy-Schulze rule. The rule states that the greater the valence of the flocculating ion added, the greater is its power to cause precipitation. Let's see an example. The coagulating power of different cations to coagulate a negative sol follows the order aluminium 3+ ions greater than barium 2+, greater than sodium+. This shows that tripositive ions are more effective than dipositive and unipositive ions. Similarly, the coagulating power of different anions to coagulate a positively charged sol decreases in the order FeCN6 4- greater than PO4 3-, greater than SO4 2-, greater than Cl-. The coagulation of a sol by an electrolyte does not take place until the electrolyte added has a certain minimum concentration in the solution. The minimum concentration of an electrolyte in millimoles per liter required to cause a sol to precipitate in 2 hours is called its coagulating value or flocculation value. It is important to note that the smaller the flocculation value, the greater is the coagulating power of the electrolyte. You can see from the table that the aluminium 3+ cation and the FeCN6 4- anion have extremely low values of coagulation power. Therefore, they exhibit greater coagulating capacity as compared to other ions in their category. Lyophilic salts, on the other hand, are much more stable than lyophobic salts and do not get coagulated easily under similar conditions. The two factors responsible for the stability of lyophilic salts are the existence of the same charge on all the colloidal particles and the extensive solvation of the colloidal particles of a lyophilic sol. A lyophilic sol can be coagulated either adding an electrolyte or a suitable solvent. A higher concentration of an electrolyte is needed to coagulate a lyophilic sol than is needed to coagulate a lyophobic sol. When solvents like alcohol or acetone are added to hydrophilic sols, the colloidal particles get dehydrated. Under this condition, a small quantity of electrolyte is able to bring about coagulation of the hydrophilic sol. Let us now discuss the protection of colloids. You already know that lyophobic sols, such as metal sols, are very susceptible to coagulation or precipitation. The process of protecting them from coagulation is referred to as protection of colloids. It has been observed that in the presence of certain lyophilic colloids, lyophobic sols acquire greater stability. They do not get coagulated easily when an electrolyte is added. A layer of lyophilic sol particles around the lyophobic sol particles prevent them from coagulating. The sheath of solvent molecules of the lyophilic colloid prevents the particles of lyophobic colloids from aggregating at low electrolyte concentrations. For example, adding gelatin, a lyophilic colloid, to gold sol, a lyophobic sol, protects the gold sol from getting coagulated if a small amount of sodium chloride solution is added. Emulsions are liquid-liquid colloidal systems in which both the dispersed phase as well as the dispersion medium are liquids. An emulsion may be defined as a colloidal dispersion of two immiscible or partially immiscible liquids, in which one liquid acts as the dispersion medium and the other as the dispersed phase. In most emulsions, one of the liquid is water, while the other is a hydrocarbon and is referred to as oil. Depending on the nature of the dispersed phase, emulsions are broadly classified into two types. They are oil and water type emulsions and water and oil type emulsions. In oil and water type of emulsions, oil acts as the dispersed phase and water acts as the dispersion medium. For example, milk is an emulsion of liquid fat globules dispersed in water. Another well-known example is that of vanishing cream. In water and oil type of emulsions, water acts as the dispersed phase and oil acts as the dispersion medium. For example, butter is an emulsion of water dispersed in fat. Other common examples of this type are cod liver oil and cold cream. Emulsions are generally unstable and separate in two layers on standing. Thus, To stabilize an emulsion, small quantities of certain other substances called emulsifiers or emulsifying agents are added. Emulsifying agents stabilize an emulsion by reducing the interfacial tension between the two phases. Proteins, gums, natural and synthetic soaps, detergents, etc. are the principal emulsifying agents for oil and water type of emulsions. Similarly, heavy metal salts of fatty acids, long-chain alcohols, lamp black, etc. are used for water and oil type of emulsions. Emulsions exhibit properties similar to colloids, like the Tyndall effect, the Brownian movement, electrophoresis, coagulation or de-emulsification on the addition of electrolytes, and so on. Emulsions can be diluted by adding any amount of the dispersion medium, that is, water for oil in water type emulsion and oil for water in oil type of emulsion. On the other hand, if the dispersed phase is added to an emulsion, it forms a separate layer. An emulsion can be separated into its constituent liquids by boiling, freezing, centrifuging, electrostatic precipitation, etc. A well-known example of centrifuging is the separation of cream from milk. Finally, let's see some important applications of emulsions. A large number of pharmaceuticals in the form of lotions, creams and ointments, which are oil in water or water in oil type of emulsions, are prepared to facilitate easy absorption by the body. The cleansing action of soap is based upon the formation of an oil in water emulsion. The concentration of ore by the froth flotation process is based upon the treatment of the powdered ore with an oil emulsion. Milk, which is an important constituent of our diet, is an emulsion of liquid fat droplets in water. The digestion of fats in our body takes place by the process of emulsification. Asphalt, emulsified in water, is used for building roads without the necessity of melting the asphalt. Colloids play a very important role in nature and in our daily life. The food we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspapers we read are all largely composed of colloids. Let us now discuss some important applications of colloids in day-to-day life. Have you ever wondered as to why the sky appears blue? The sky is the empty space around the earth and has no color as such. It appears blue due to the scattering of blue light by the dust particles and the water suspended in the air. Seawater also looks blue for the same reason. The colloidal impurities in seawater scatter blue light. The Tyndall effect of scattering of light by colloids is responsible for the blue color of the sky and the seawater. Do you know that some of the food we eat is colloid? milk, halwa, butter, ice cream, fruit juices, jellies, etc. are colloids in one form or the other. For example, milk is an emulsion of fats in water, while ice cream is a dispersion of colloidal ice particles in cream. Another very important colloidal solution is blood. Bleeding from a fresh cut can be stopped by applying a concentrated solution of ferric chloride or potash alum. The negatively charged colloidal particles of blood get neutralized by the ferric or aluminium 3+ ions, resulting in the coagulation of blood. Fog, mist, and rain are all colloidal in nature. In winter, at night, the moisture in the air condenses on the surface of dust particles, forming tiny droplets. These droplets, being colloidal in nature, float in the air, forming mist or fog. It is interesting to note that even clouds are colloidal systems. Clouds are aerosols consisting of small droplets of water suspended in air. Due to condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. It is worth noting that a natural disaster of cloudburst is believed to occur due to the mutual discharge of oppositely charged cloud particles. A cloudburst results in a very heavy downpour in a short period of time. We also come across the term artificial rain. Clouds, as we now know, are colloidal, carrying some electrical charge. Clouds can be made to cause rain by spraying oppositely charged colloidal dust or sand particles or precipitates of silver iodide over them. The neutralization results in coagulation of the water droplets, which come down in the form of rain. This type of rain is called artificial rain. Another interesting example is the formation of a delta at the mouth of a river, when it meets the sea. River water is a colloidal solution of sand and clay, which carry a negative charge. Sea water contains a number of electrolytes of sodium, magnesium, and calcium. When river water comes in contact with sea water, the positively charged ions of the electrolytes coagulate the negatively charged colloidal particles, which settle down. The level of the riverbed rises, forcing the stream of water to split. This happens again and again, and over time the river takes the shape of a delta. A noteworthy example you are already familiar with is the cleansing action of soaps. Soap solutions are colloidal in nature. They remove the dirt and oil particles either by adsorption or by emulsifying the greasy matter sticking to cloth. Let us now look at some industrial applications of colloids. The most important industrial application of colloids is the Cottrell smoking precipitator. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, and dust. Smoke from industries is a major air pollutant, and therefore it is desirable to precipitate it to prevent it from spreading. The Cottrell precipitator precipitates smoke on the principle of electrophoresis. smoke is allowed to pass through a chamber with a number of metal plates. These metal plates are attached to a metal wire connected to a source of high potential of about 30,000 volts. The charged particles of smoke get attracted by the oppositely charged electrodes or metal plates and fall to the bottom after getting discharged. The clean hot air passes out through the chimney, thereby reducing pollution. Another important application of coagulation of colloids is the purification of water. Water from natural sources often contain impurities that are colloidal in nature. Precipitating these colloidal impurities can be carried out by adding certain electrolytes like potash alum or aluminium sulfate. The negatively charged colloidal particles of the impurities get coagulated by the action of the aluminium 3+ ions furnished by the electrolyte and settle down. Pure water can then be filtered or decanted off. Yet another application of colloids is in medicines. Colloidal medicines are more easily assimilated by the body system, as they can act over a large surface area. Therefore, they are more effective. It is for this reason that a large number of pharmaceutical preparations are emulsions. For example, milk of magnesia used for stomach disorders. Cod liver oil and skin ointments are all emulsions. Some important salts that are commonly used as medicines are argirols, a silver metal sol used as an eye lotion. Colloidal antimony used for curing Kala-Azar. And colloidal gold used for intramuscular injections. It is important to note that antibiotics are usually injected into the body in colloidal form. Another industrial application is in the leather tanning industry. Raw skin hides of animals contain positively charged colloidal particles. When a hide is soaked in negatively charged tannin and compounds of chromium, mutual coagulation takes place in the pores of the hides. This results in the hardening of the leather. The process is called tanning. The principles of colloids and interface signs are used for the successful formulation and manufacture of photographic products. The color-forming components are usually delivered in colloidal form. Photographic plates and films are prepared by coating an emulsion of light-sensitive silver bromide in gelatin over a glass plate or a celluloid film. Another application of colloidal salts is in the rubber industry. Latex obtained from rubber trees is an emulsion consisting of negatively charged rubber particles in water. Rubber is obtained by the coagulation of latex. This coagulated mass is later subjected to vulcanization and is sold as rubber. We have discussed a number of applications of colloids in life and in industry. Furthermore, inks, paints, lubricants, synthetic plastics, cement, smoke screens are all colloidal solutions. Sewage disposal also makes use of the phenomenon of electrophoresis, as sewage water is colloidal in nature.